So we're back. Uh, is this recording? Yes, that's recording. We're back. We're back in Germany. My background's going to be different for a while now. Yeah. Anyway, I guess if you're watching this, probably you know that this project won the contest that that Karpathy, if I'm pronouncing his surname correctly, posted on X recently. I haven't really made an official sort of thank you message yet, but I will at some point. I just wanted to, because my schedule is very tight. I just wanted to kind of at least get those like 20 minutes of like focus and grinding time, because otherwise I'm never going to get done with even one problem. Okay, so we've got 12 videos for this problem, and we're kind of getting slowly to the solution, but it's not there yet. And let's see, let's hope that we're gonna get a little more, and I'll just jump straight to it, okay? And then I'll make a proper nice thank you video announcement, whatever next steps, because I think this project has a lot of potential, but I don't want to waste time right now. We were constructing this group in here, and I think Grog got stuck maybe, but I'll just do a fresh. To sum it up, 3 to the power of 1 plus 2, here will be a P group, geocenter G over 3. No, okay, we'll just do a new conversation. So G with order 9, and a quotient of order 3 exactly. And we'll go auto mode. Yes, the statement is correct. Cool. Verification. Properties, quotient group is 3. So it's non-trivial is the power of P. Yes, but that's all good. All right. Can you construct an example, or can you construct an example? Can you construct this group? Or an example? Because I don't know. I guess this is a type of group. You know what I mean? That's not a very specific group. I think there's multiple groups that fulfill all these, and they're all 3, 1 plus 2 groups. So can you construct an example of this group using SymPy? And be as verbose as you can when it comes to defining, I think they were called relations. Relations, restrictions, rules, I forgot. So I can follow along. Sorry, because I'm changing setup. I'm just hoping that it's recording everything correctly. Yeah, all good, cool. Let's see what it gets. Yeah, so essentially it's just saying the center. I'm curious how it's gonna map these this constraint. I'm curious how it's gonna do these. Boy. I think one of the things, and I'm curious to see what happens when I get to the end of one problem. I think overall, working with an LLM like this in the loop is really not that bad. It's not that bad if you have consistency and you kind of do a little bit every day. And it's more about like how do you stay motivated? like you can clearly go fast. I would have never been able to figure something like this without the LLM because I don't know any of these concepts. So I would have to go and either Google stuff or find a textbook or something like this. And even then, it's just like I wouldn't have been able to generate like code, which generating code is, at least for these type of problems, for me, it's very helpful because code kind of sometimes brings you one level below the abstraction, and it kind of like helps me then understand the abstraction itself, right? Because you're like, okay, that when you have an example, then it's, don't get me wrong, you always have to try to understand the abstraction, but it helps to kind of go from top to bottom and bottom to top again. I do think that branching, and I know I haven't tried any LLM chat that has branching. I know that there's things like T3 chat and a few other uh, provider agnostic chats have cool features like branching. This would help, I think, because the biggest challenge so far has been in kind of consolidating a concept. Like I would in a video typically like think, oh yeah, okay, cool. So I would kind of understand something at like an 80%. And then I would do the next video and the next day, and I'm like, that rings a bell. Yes, I knew what that meant, but I don't remember it. How do I recall it quickly, right? And then I think this would be something that if the editor had like some built-in, I don't know if it's maybe a glossary or something like that, where, you know, maybe the one thing that could be interesting is analyzing each of these videos, right? As I publish the video, do an AI analysis on each of these videos, and kind of maybe get something ready for next session. You know what I mean? These could be a thing, because it takes, like, solving problems in the real world is hardly something that happens in one sitting. You're always gonna work on these and kind of go back and forth. You know, you work on it for an hour, then you work on it for like half an hour the next day, or even like 2-3 hour straight. That's all fine, right? But like maybe even within one long session, that probably happens, right? If you're, you know, kind of I was thinking a lot. Let's see what happens. You're kind of you know, discovering and establishing some of the concepts in your head in the first 10 minutes, and then maybe 3 hours down the road, you've kind of forgotten about those specific things. There's always something that is left in your head, like a trace that you've visited that concept, but it's something that it's sometimes just hard to come back to. And because it, specifically Grok at least, but it happens with a lot of LLMs, I guess, they tend to be verbose, right? Because that's, I guess, that's, yeah, like, and you don't want to kind of have to read all this stuff right away. So just, if you're just trying to do recall, you know what I mean? What? Oh, yeah. Yes, that's true. So it actually corrected me. That's good. It's order 27, and then this is order 9. No. The order of the center. Why is the order of the center 9? The order, no. Okay, no, let me, no. Let's go back to these. Can I think I can just edit that. I don't know if that acts as a, no, let me edit this one here. Of order, the center, a group G with order 27, and center the G of order 9. That is correct, because this is 3 squared. That's what the center is. Or is that's what the center is. That's what the center is. 3. And then center 3, order 27, the center ZG is of order 3, exactly, and the quotient is of order 9. Yes. Okay. Yeah, that kind of branched the whole thing. Okay, there is branching. So I can go to the previous message and I see everything. Yeah, okay, but I kind of lost the follow-up messages. So I'm here now. Yes, it makes sense. Cool. Build me an example with SymPy code. And now it's going to do longer thinking. And so, guys, I'm actually half multitasking here, so and that's also what you shouldn't be doing, but I can't. I have to do it this way. I'm sorry. All right. While it's thinking, okay, I'll be back in a second, guys. Okay. Yeah. Sorry, guys. There we go. It's still thinking. Yeah, it's still thinking. Right? Oh no, it's already done. Sorry. Okay, that's good. Let's run it first. First, we'll run it, see if it works. Okay. Okay, it does work. Wait, isn't it supposed to be a billion? What did it mean to be? No, a billion. It meant that it's a billion. It meant that it's cumulative with everything, right? That's the point. That it's not. So center consists of elements G such that yeah, exactly, for all. So that's okay. So that's checking for that. How's this defining it then? Okay, so define the Heisenberg group Z over 3, Heisenberg multiply. So it's defining these group triples. And the group operation is a trip, basically A plus 1, B plus 1, C. Whoa, okay. What is that? What is that? So A1 plus A2, B1 plus B2, and then C1 plus C2 plus A1 times B2. The Heisenberg group over Z3. So generate all elements of the group. So list basically all the triples. Create a list of permutations to represent the group. Okay, so here calculating all the products of G and H and is doing the permutations. Permutation group. Create a permutation group, permutations. G in elements. Okay, so these are the elements. And it's just calculating that. Okay. All right. The other group is 27. The center consists of elements G such that G times H equals H times G for all H. The center falls. Okay, so it's just fine. But how has it constructed it? How did it know? That's intuitively speaking. I guess you know that not everything is going to commute, right? Because obviously here you have an a1 times b2, a1 times b2. So if you just swap it, that's only going to work for those cases where you have a 0 or something like this, which kind of makes sense because this is also what the result says. I think the center has zeros in a1 and b2s, I think, something like that. Yeah, because then of course it commutes. Okay, but I need to, how has it actually built that? Is the Heisenberg group, I keep seeing that, I keep seeing Heisenberg group all the time all over the place, and I don't know what is that group. So what is the Heisenberg group in group theory? In quantum mechanics, I was going to say, captures the structure of certain computation relations like those of position and momentum operators. Ah, okay. The group matches multiplication. Okay. Okay. Ah, look at this. That's the operation. That is the operation. Non-abelian, key properties. And that appears models of commutation relations of position and momentum operators in quantum mechanics. Okay. Yeah, the intuition is the important thing. Think of that as a mathematical structure that formalizes the idea of position and momentum not commuting. Okay. The extra coordinate C or T in the group operation keeps track of this non-commutativity, making it the prototype for non-abelian groups that are close to being abelian. If you want a deeper, okay, fine. No, I guess I get it. It's like the position and momentum not commuting. That is the quantum stuff, quantum mechanics stuff. But I mean, okay, fine. How did it know that though? Well, okay, whatever. Like, find the center G. That's all fine. Verify that exactly. Verify G is not abelian. Yeah, that's all good. So we have something. Let's keep that. Now, now let's ask the following question, right? Because that's the important part. Is if I want to ask for these, so how would that definition change if now I want to build a group with an extra restriction expressed by a sub-index plus. So this group, I need the raw question. This is what we want to have. Here. The plus subscript in the context, the plus indicates that the group is the extra special group of exponent P, as opposed to the other extra special groups of order P3, which has exponent P2 and is sometimes denoted as okay. Really? To an elementary abelian group of order P. Here n equals 1. So the plus restriction specifies that the group has exponent 3. Every element G satisfies G3 equals 1. So it would still be the same, wouldn't it? What if it was a minus instead? exponent p, 2 equals 9. What? This group still has a center of order 3 and a quotient of order 9, but the key difference is that some elements have order 9 reflecting the higher exponent. Has order 9. I don't understand. The group S has exponent 9. This means some elements G of S satisfy G9 equals 1, but not necessarily G3 equals 1. Why is this expressed as plus or minus in the subscript though? The two non-isomorphic extra special groups based on their exponent and structural properties. The representation or properties like the exponent. Let's dive into why. So it's a non-abelian group with the center 3 with the, exactly. The property of the commutator subgroup equals to the center, and the center is cyclic. So if p equals 3, there are exactly two non-isomorphic extra special groups of order 27. The group is because there are two exactly. Okay. Yeah, okay. Exponent, least common multiple of the orders of all elements, and sometimes their structural algebraic properties. This group has exponent 3, meaning every element G satisfies that G3 equals 1. This group has exponent 9, meaning some elements satisfy G9 equals 1, but not necessarily G3 equals 1. Okay, it's just to, okay. So we have an extra restriction that says that all elements have G3, have an exponent or an order of G3 equals 1. Okay, then give me the code that represents the plus 1. I guess that's what it is. I mean, I don't know. At this point, I don't want to go down this rabbit hole too much because I want to actually finish the problem. But it's just a way to say, cool. So you have this group, then the 1 plus 2 gives you a certain structure, and then the plus minus also helps you differentiate. It's just, I guess, it's just notation of these different groups. That's all fine. So let's just preview that and see the code actually does check for the plus somewhere, right? Yeah, verified exponent is 3. If we have that, we're done for today. And then the next, yes, all the elements satisfy these. False, we're good. Okay, we're good. Then we're good. Then we have that. And now, but okay, like how would you like? It's still a black box to me. How would you even come out with this group though, in the first place? How would you even build that group like this? I think the way these groups were discovered is the other way around, right? So you study things and then like, okay, can I represent that in an abstract way, and then finding isomorphisms between different fields and whatnot. But I still, how would you find that? How would you actually come up with it? How would you construct this group? And here's where I need to kind of go back and say, cool, so you have this is this P thing where I even forgot. I mean, the P group is big, right? Because is what was the definition of P group again? Um, yeah, it's a group whose order is a power of P. Okay. Yeah, so that's very generic, right? And then you're adding constraints. It's all right. Okay, well, let's not die on that. Let's not like boil the ocean there for now. We got these, and we construct these, and now, yeah, we can figure, like, it's fine. We can figure. I don't know if we need to understand that too much into detail. But the question is, now we need to do S times D. Now we need to do S times D and then define the action, right? And define the action that is based on that, induced on that permutation stuff. Fuck, man, this is so complicated. Boy, slowly, we're gonna get there. We have to stay strong. See you in the next video.